So welcome to class number 4 of basic electronics. First today we will revisit the classification of materials based on conductivity. So we discussed that based on conductivity we have three types of materials. One is metal, which has a very high conductivity. The second is semiconductors, which have moderate to low conductivity, and the third is insulator, which have zero or near zero conductivity. Now, since we have learned about band and band gap, we will revisit these things from the perspective of band gaps. So, a material may have at least one partially filled band at 0 Kelvin. So, we have noted earlier that an empty band doesn't conduct, also a completely filled band doesn't conduct. So, semiconductors, in case of semiconductors or insulators, the bands are either completely filled, other bands are completely empty, so it doesn't conduct at 0 Kelvin temperature. Okay, so in case of metals, there is at least one partially filled band at 0 Kelvin, and that is why metals can conduct at 0 Kelvin. So this type of material constitute metals. And then the second class is that there can be only completely filled or completely empty bands. At 0 Kelvin. So there are no partially filled bands at 0 Kelvin temperature. So for this kind of materials, if the band gap is comparable to 1 electron volt, then at room temperature these materials behave as semiconductors. Of course, at 0 Kelvin these materials behave as insulators because the bands are either completely filled or completely empty, but at room temperature these materials behave as semiconductors. At room temperature these behave as semiconductors. Okay, and then in case where the band gap is higher, that is greater than 3 or 4 electron volts, then at room temperature these behave as insulators. Okay, why do the materials behave as semiconductor when the band gap is comparable to 1 electron volt? Is because if the band gap is comparable to 1 electron volt or less than or slightly more than 1 electron volt, then it is much easier for the electrons to absorb thermal energy and get excited from the valence to the conduction band. Okay, once the electrons get excited from the valence band to the conduction band has a few electrons now, so the conduction band would conduct. The valence band also has a few holes now, so the valence band would also conduct. So at room temperature, this kind of materials can actually conduct current. On the other hand, if the materials have a higher band gap, that is greater than 3 or 4 electron volts, then it is not easy for the electrons to absorb thermal energy and get excited from the valence to the conduction band, because 3 to 4 electron volts is actually a large energy. So in that case, if the band gap is higher than 3 or 4 electron volts, it is not very easy for the electrons to actually absorb energy or absorb thermal energy and get excited from the valence to the conduction band. So in that case, in room temperature also, the valence band of these materials are completely filled and the conduction band of these materials are completely empty. Okay, so at room temperature, these materials exhibit zero or near zero conductivity, and these materials are known as basically insulators. Okay, I hope it is clear to all of you now. Now let us get back to our previous discussion. We noted that in the second class that one of the attractive properties of semiconductor is that their conductivity can actually be enhanced by adding impurities. Okay, so the conductivity can be enhanced by adding impurities, and we discussed earlier that this is the property of semiconductors that make it so attractive in the semiconductor industry or in electronics industry actually. Okay, so in this case, the impurities basically mean any material which is not the semiconductor itself. For example, if I introduce phosphorus in silicon, then phosphorus is actually an impurity to silicon. Okay, if I introduce phosphorus in silicon, then that material is not pure silicon. That material is impure silicon actually. Okay, and the process or the phenomenon of actually enhancing the conductance or the conductivity of semiconductors by introducing impurities is known as doping. Okay, so the phenomenon of enhancing the conductance or conductivity of semiconductors by introducing impurities is known as doping. Now then there are intrinsic semiconductors or pure semiconductors. Intrinsic or pure semiconductors. So in this kind of semiconductors, impurities are not added. That is, these are not doped semiconductors. So intrinsic semiconductors are basically pure semiconductors. In this kind of semiconductors, no impurity is added to enhance its properties, and these semiconductors have the properties of the semiconductor itself. For example, intrinsic or pure semiconductor has the properties intrinsic or pure silicon has the properties of silicon itself and not of any other material. Okay, now then on the other side of intrinsic semiconductors, there are extrinsic semiconductors. So in case of extrinsic semiconductors, impurities are actually added to enhance the conductivity of semiconductors. So these are also doped semiconductors. Okay, and these are also known as impure semiconductors, extrinsic or impure semiconductors. Okay, example is introducing phosphorus in silicon. So now we have done a few definitions. Let us understand how does doping enhance the properties or enhance the conductance or conductivity of a semiconductor. So let us consider this crystal structure of silicon which is doped with phosphorus. So one phosphorus atom is sitting in between all these silicon atoms, and whenever I talk about doping, this doesn't basically mean that you introduce a lot of impurities into semiconductors. Okay, so the maximum limit of impurity that you can introduce in semiconductors is around 1 or 2%. Okay, when you, for example, introduce phosphorus in silicon, you do not generally introduce 50% phosphorus into silicon. You just introduce a maximum limit of 1 to 2% of phosphorus into silicon. 2% is kind of the maximum. It is very high actually for an impurity doping, but generally you introduce a maximum limit of 1% of phosphorus atoms actually. Okay, so you do not introduce, let us say, 10% of phosphorus in silicon, but you introduce a maximum of 1% or a maximum of 2% in exceptional cases phosphorus in silicon crystal structure actually. Okay, so let us consider that this phosphorus atom is sitting and it is surrounded by the all these silicon atoms. Okay, now this phosphorus actually has 5 electrons in its valence shell. Phosphorus is actually a group 5 element. A group 5 element means that the phosphorus atom should have 5 electrons in its outermost shell. Okay, but it is sitting in the silicon crystal structure. Okay, it is sitting in the silicon. The mother material is actually silicon, and it is, let us say, doped with 0.25% of phosphorus or 0.5% phosphorus. Okay, so it is actually sitting in the silicon crystal structure, so it is surrounded by silicon atoms. So basically what is happening here is phosphorus is replacing a silicon atom here. For example, there could have been a silicon atom here in case of pure silicon crystal structure, or let us say in case of undoped silicon crystal structure, and it would have been bonded with the neighboring silicon atoms like this. But what phosphorus is doing, phosphorus is basically replacing this silicon in the crystal structure, and it is now sitting here. Okay, so instead of silicon, the phosphorus atom is sitting here. Now phosphorus is actually having 5 electrons in its outermost shell, but it is only surrounded by 4 nearest silicon atoms. So one is this silicon atom, this silicon atom, this silicon atom, and this silicon atom. Okay, so it is surrounded by 4 nearest silicon atom, but phosphorus has 5 electrons in its valence shell. So out of those 5 electrons, 4 actually participate in bond formation with these 4 neighboring silicon atoms. Now 1 electron is now left free. Okay, now this electron doesn't have any electrons from neighboring atoms to bond, because phosphorus is surrounded by 4 nearest silicon atoms. Okay, so this extra electron doesn't have or doesn't get another electron to form a bond. Okay, for bond formation you need 2 electrons. So this extra this extra electron here doesn't get another electron to form a bond, and so this kind of remains as free electrons. This electron actually have a much higher energy compared to these electrons of phosphorus which have taken part in bond formation here. Okay, so this fifth electron in phosphorus doesn't get another electron to form a bond, and so this has a higher energy and this remains as a free electron. And at room temperature, because this electron has a higher energy than rest of the electrons of this phosphorus atom, this electron is going to reside in the conduction band. Okay, so what I mean here is that one phosphorus atom actually, or each phosphorus atom actually adds one electron to the conduction band of silicon. Okay, that is the fifth electron of phosphorus. Okay, I again repeat that phosphorus has 5 electrons in its valence shell, and out of those 5 electrons, 4 electrons participate in bond formation with the nearest 4 silicon atoms. Okay, the fifth electron cannot participate in any bond formation, and therefore it is more like a free electron. It doesn't belong to any particular silicon atom, or it doesn't remain bonded to any particular atom, but it is basically dispersed, more like dispersed throughout the crystal, and this has a higher energy, and this mainly reside in the conduction band. Okay, so each added phosphorus atom contributes to 1 electron in the conduction band. So if I add, let us say, 100 phosphorus atom, that contributes to basically 100 electrons in the conduction band, approximately, that is. Okay, so in the limit that the dopant concentration, or the concentration of phosphorus atoms, let us call that Nd, is much greater than Ni. Ni again is the intrinsic concentration of electrons in the conduction band, and Ni is basically fixed for a given semiconductor at a given temperature. Okay, Ni is the concentration of electrons in the conduction band for a intrinsic semiconductor. Okay, and it is a property of the semiconductor itself. So each semiconductor is going to have a fixed Ni at a fixed temperature. Okay, so given that the concentration of dopant atoms, let us say concentration of phosphorus atoms, given that the concentration of phosphorus atom is much larger than the intrinsic electron concentration in the conduction band, given that the concentration of phosphorus atoms is much greater than the intrinsic electron concentration of electrons in the conduction band, we have the total concentration of electrons in the conduction band to be approximately equal to Nd. Okay, so this is N is the total electron concentration in the conduction band. So let us take an example. Let us say that Ni is 1.5 into 10 to the power 10 per centimeter cube. Okay, so this is the intrinsic electron concentration in the conduction band for silicon at 300 Kelvin temperature. Now let us consider that we have doped this silicon. So for silicon at T equal to 300 Kelvin. Now let us assume that we have doped this silicon with phosphorus, and we have doped it with let us say 10 to the power 16 per centimeter cube of phosphorus atoms. Okay, so this condition that Nd much greater than Ni holds now. Now, just as before, each of these phosphorus atoms is going to contribute approximately 1 electron to the conduction band. So, 10 to the power 16 per centimeter cube of phosphorus atoms is going to contribute 10 to the power 16 per centimeter cube electrons in the conduction band of silicon. But earlier, this concentration, the intrinsic carrier concentration, was 1.5 into 10 to the power 10. So, assuming that the total electron concentration is approximately Ni plus Nd, well, this is not the exact correct formula, but let us assume that the total electron concentration is the sum of the intrinsic carrier concentration plus the electron concentration contributed by the phosphorus atoms. Okay, let us assume it for the time being, assuming that N is approximately equal to Ni plus Nd. We have N approximately equal to Nd since Ni is much less than Nd. Okay, so this is a logical argument, but I again repeat that this formula is not entirely correct, so don't take this too seriously. This is just for your understanding that when the concentration of dopant atoms is much greater than the concentration or the intrinsic carrier concentration of the semiconductor, then the total concentration of electrons in the conduction band is approximately equal to the dopant concentration. Okay, this kind of dopants which add electrons to the conduction band are known as N-type dopants. Okay, and this N-type dopants, or these are also known as donor dopants. Donor dopants in the sense that they donate one electron, each atom actually donate one electron to the conduction band. That is why they are known as donor dopants. Okay, or N-type dopants because they again donate electrons to the conduction band, and electrons have a negative charge. So this N basically represents negative. Okay, so these are known as N-type dopants. So impurities that donate electrons to the conduction band of semiconductors. Generally, these belong to group 5 elements. For example, phosphorus is one N-type dopant. Then there are other N-type dopants also. For example, arsenic, nitrogen, these are also N-type dopants. But the most widely used N-type dopant is actually phosphorus. Okay. Similarly, we can also introduce another kind of dopants which belong to group 3. Okay, these are mainly known as p-type or acceptor type dopants. And these introduce holes in the valence band of semiconductors. Okay, so these are generally group 3 elements. And classic example would be actually boron. Boron is a group 3 element, and then there are others such as aluminium, indium, gallium, etc. So boron is actually the most widely used p-type dopant or acceptor type dopant. Okay, and let us see that how introducing boron actually contributes to enhancing the number of holes in the valence band. Now this diagram again shows bonded silicon atoms, and one boron atom is actually, let us assume, sitting in between them here. Now boron only has 3 electrons in its outermost shell, or 3 valence electrons. Now these 3 electrons actually form 3 bonds with the neighboring silicon atoms. So the 3 electrons in the valence shell of boron has formed 3 bonds with the neighboring silicon atom, but with the 4th silicon atom, which is also a neighboring atom, there is no bond formation, because boron actually has exactly 3 electrons in the valence shell. So there is no bond between this boron atom and this silicon atom over here. Okay, so but the silicon atom here has actually 4 electrons in the valence shell. So the 4th electron in this silicon doesn't take part in the bond formation. So this remains like a free electron. Okay, this is not a bonded electron. Now what might happen is that one electron, so this electron is like a free electron, one electron from this bond might actually come and form this bond over here. Now this one electron from here, from this bond, might break and come to this position. So now this bond is complete because it now has 2 electrons, but this bond has remained unsatisfied. So this bond here now contains 1 electrons, because an electron has moved from this bond to this bond over here. Okay, then an electron from this bond might actually transfer, this bond might break, and 1 electron from this bond might transfer to this location. So this bond has 2 electrons now, and this bond has 1 electron now. Okay, so in this way these electrons actually move around, and as we discussed earlier, that broken bonds are basically like holes, not like holes, but broken bonds are basically holes. Okay, if there is an unsatisfied bond, that contributes to holes. Okay, so since this bond is unsatisfied, or let us say initially the bond with this boron atom and this silicon atom was unsatisfied, the introduction of boron atoms in silicon basically introduces holes in the valence band. Okay, if I introduce boron in silicon, this would introduce unsatisfied bonds, or this would introduce half satisfied bonds, let us say. So introduction of boron in silicon basically introduces holes in the valence band. Okay, and that is why they are known as acceptor type impurities, because a boron atom has 3 electrons in the valence shell, so it can actually accept 1 extra electron and form a complete bond with the neighboring silicon atom. So in that sense, since it is accepting 1 electron and forming the 4th bond with the neighboring silicon atom, that is why these are known as acceptor type impurities. And these are also known as p-type impurities or p-type dopants. This is because holes are assumed to have a positive charge actually. Why? Because holes basically come when electron, or when a bond breaks and the electron actually excites to the conduction band. Okay, so initially the valence band was completely filled, and everything was neutral. Now an electron from the valence band escapes to the conduction band. So in the conduction band there is one negative charge, which is the electron, and since there is a negative charge in the conduction band now and everything is neutral, there is a hole in the valence band, and that hole must be positively charged because everything has to be neutral. Okay, so holes are assumed to be having a positive charge. So let me write it here. Holes are assumed to have a positive charge, and that is why these kind of donors, not that is why, but holes are assumed to have a positive charge since these impurities introduce holes in the valence band. They are known as p-type dopants. P for basically positive, actually positive charge. So I repeat again that initially the valence band was completely filled, everything is neutral. Now an electron from the valence band has been excited to the conduction band, and the conduction band contains one negative charge. Now since everything is neutral, the valence band must have one positive charge. Okay, so the valence band have one hole, and that hole is assumed to have the positive charge here. Okay, this is just a vacancy of electron. Okay, and holes are assumed to have positive charge. Okay, so that is why these are known as p-type dopants. Now just as the previous case, assuming that the concentration of these acceptor type impurities, which we denote as Na, okay, Na is the concentration of acceptor type impurities. This A basically denotes acceptors. Okay, if Na is much greater than Pi, Pi again is the whole intrinsic hole concentration. In this case, we have P approximately equal to Na by the same logic as before. P is the total hole concentration in the valence band. Okay, and then we have the law of mass action. This law of mass action basically states that the product of the total number of electrons in the conduction band and the total number of holes in the valence band is equal to the product of the intrinsic electron concentration in the conduction band and the intrinsic hole concentration in the valence band. Okay, so we will not go into too much detail how this law came about, but just know this law. Some small mathematical problem might be asked that uses this law. Okay, finally, before we go into the actual devices, or we study the actual devices, let us discuss a few more parts. So current flow in semiconductors. There are two main mechanisms of current flow in semiconductors. The first mechanism is that you apply an electric field and the electrons start moving in response to the electric field, because electrons are basically charged particles. Or let us say you apply an electric field and the holes start moving in response to the electric field, because I repeat again that holes have basically a positive charge. Okay, so this kind of current that flows in response to the electric field or that flows due to the electric field is known as the drift current. Okay, so here the driving agent is the electric field, and electrons and holes flow in the opposite and same direction as the electric field respectively. So electrons have a negative charge, so they move opposite to the direction of the electric field. Holes on the other hand have a positive charge, so they flow in the direction of the electric field. And the other current component is basically known as the diffusion current. So this kind of current flows due to a concentration gradient of carriers. For example, if you spray perfume at one corner of the room, after some time the entire room starts smelling with perfume. So here what has happened is that you sprayed perfume at one corner of the room, and at that corner there is a very high concentration of perfume molecules, and these perfume molecules gradually start moving from the point of high concentration to the point of low concentration. Okay, or let us say if you put one drop of ink in water, gradually that ink gets dispersed throughout the water, and after some time the entire water becomes colored. So here what has happened is that when you put one drop of ink in one corner of the water, that area has a very high concentration of those ink molecules, and these ink molecules gradually flow from the point of high concentration to other points with lower concentration, and that is how gradually this ink gets dispersed throughout the water and the entire water becomes colored. Okay, so similar is the case of electrons. When we have high concentration of carriers at one end of the semiconductor and low concentration of carriers at the other end of the semiconductor, these carriers start flowing from the point of high concentration to the point of low concentration, and this flow that occurs due to a difference in concentration of carriers is known as the diffusion current, or constitutes the diffusion current. Okay, so electrons or holes flow from the point of high concentration to the point of low concentration, and this flow occurs due to a difference in carrier concentration or a gradient in carrier concentration. Okay, so this is known as the diffusion current, and why it is known as the diffusion current is because carriers diffuse from the point of high concentration to the point of low carrier concentration. Okay, so that is why this is known as diffusion current. Here, the driving agent of current flow is basically the concentration gradient of carriers or the concentration difference of carriers. Okay, so concentration difference of carriers or concentration gradient of carriers means spatial difference or spatial gradient. So there should be a spatial difference in carrier concentration or a spatial gradient in carrier concentration. Okay. Now let us examine the formula or the equation for the drift current. We know that the velocity of a charged particle is actually proportional to the electric field. Okay, so let us assume that Vd is the average velocity with which the carriers are moving. Of course, under the influence of the electric field. Okay, so here this term carrier basically means electrons or holes, the current carriers, that is. Okay, now let us assume that mu n or mu p is the average drift velocity of the electrons or holes per unit electric field. So as I said that the average velocity or the velocity of a charged particle is actually proportional to the electric field. Okay, so mu n or mu p is the average drift velocity of electrons and holes when the electric field is unity. So the drift velocity must be equal to the average drift velocity per unit electric field times the electric field, right? So this Vd is basically the let us call it Vdn because we have used the mobility of electrons here. Similarly, the drift velocity of the holes in the valence band is equal to the mobility of is equal to mu p times this electric field. So mu n or mu p, this is basically known as the mobility of electrons or holes. Okay, so basically mu n here is the mobility of electrons and mu p is the mobility of holes. So this is a measure of how fast the electrons or holes can flow when an electric field is applied. Okay, so higher the value of mu n, higher velocity the electrons or holes will gain when the electric field is basically applied. Actually, we'll put a minus sign here because the electrons are moving opposite to the direction of flow. Electrons are actually moving opposite to the electric field. So Vdn, which is the drift velocity of electrons, is minus mu n times the electric field. Okay. Now the total drift current, which we call as J drift. This is the drift current density basically. The drift current per unit area. So the drift current density, this is equal to, there are n electrons and each electron is moving with an average velocity Vdn. So the total flux of electrons, or the total rate of flow of electrons per unit area, is n times Vd, and then the electrons carry a charge minus q. Okay, so when you want the current, you multiply by the flux of the particles by its charge. Okay, this is the rate of flow of electrons per unit area, and then if you want to get the current per unit area due to flow of electrons, you have to multiply it with the charge of the electron. So the total drift current due to electrons is minus q times n times Vd, and then we also have flow of holes. So the total flow of holes, or the rate of flow of holes per unit area, is P times Vd P. So the concentration of holes per unit volume times the drift velocity of the holes. So if we want to calculate the current, we have to multiply this rate of flow of holes with the charge of the holes, which is plus q here. So this is the current due to electrons in the conduction band, drift current actually. This is the drift current due to holes in the valence band. Now we just replace this drift velocity here with the appropriate formula that we have seen in the previous page. So minus q n times minus mu n e plus q times p times mu p into e. So this becomes q n mu n plus q p mu p times the electric field E. Now this quantity q times n times mu n and q times p times mu p, this quantity is also known as the conductivity, which is denoted by this letter sigma. Okay, so this is the conductivity. So conductivity sigma, so let me write the formula again here. So J drift is equal to q n mu n plus q p mu p times E. This is the conductivity sigma. And so the entire formula becomes sigma times E. So I hope that you have actually learned this equation during your 12th standard, where the current density, or the current per unit area, is equal to the conductivity times the electric field. Okay. Now you may have one question in your mind, that if I have a charged particle and I apply an electric field, the charged particle would generally accelerate. It would accelerate continuously, and its velocity would continually increase to infinity. That is what the mathematical equation states, that if I have a charged particle, for example, if I have a charge q and if I have the electric field E, then the force on the charged particle F is equal to q times E, and the acceleration is due to q times E by the mass, and so it is having a constant acceleration, and if it starts from zero velocity, it would accelerate to until infinite velocity is reached. And that is the question that might hover in your mind, that why in case of electrons the velocity is proportional to the electric field, and why in case of electrons or holes, let us say, the velocity does not go to infinity. Okay, so the answer is that this equation is the equation of a free particle. electrons are or holes are not free particles in that sense because they are surrounded by lattice atoms. When an electron tries to gain velocity and move, it is basically scattered by the neighboring lattice atoms, and that gives a force in the opposite direction. So an electron moving in a lattice crystal, or the electrons moving in semiconductor, cannot actually gain infinite velocity under the influence of an electric field, but due to scattering and due to, when, as I said, that when an electron scatters, the force is basically in opposite direction. So this is how an electron would flow. Let us say that in a schematic diagram, these are basically positions of atoms in a 1D chain of atoms. So these are basically positions of silicon atoms, let us say. An electron flows and it scatters from this atom, its velocity gets reduced, and it again accelerates due to the electric field. It scatters from this atom again and its velocity is again reduced, and then it again accelerates due to the electric field, again it scatters from this atom, its velocity again gets reduced, and again it starts from a reduced velocity, accelerates, and it reaches this atom and again scatters. So this is how an electron would flow in a semiconductor, or also in a metal, or any other substance in general. Okay, so this is how electrons would flow, and that is why when we apply an electric field, the electron flows with an average velocity, but not with an average constant acceleration. Okay, so the situation is similar to the case that if you drop a ball from a high distance or from an aeroplane, that ball would actually fall, and the air would actually give it a resistance, and this resistance given by the air is actually proportional to the velocity of the ball, and at one point of time, as the velocity of the ball keeps increasing, the opposite force due to air, or the resistance force due to air, also increases, and at one point of time the force due to gravitational pull on the ball is equal to the resistance force offered by the air, and at that point of time the ball attains a constant velocity, which is basically known as terminal velocity, which again I think all of you have learned in 12th standard. So the situation is exactly the same here, that due to the resistance offered by these atoms, or the resistance offered by this lattice crystal, the electrons cannot accelerate to infinite velocity due to the electric field, but they flow with a average velocity. Okay, so that is the case, that this is why the drift velocity of electrons is proportional to the electric field. Okay, the electrons flow with an average constant velocity, but not with an average constant acceleration. Okay, so I hope this is clear to all of you. Let us do up to here today. Thank you all.